Greetings, Doctor. My name is Kadiresan Analalaki Mohan, DF240189, and I'm from Group 3, and this is our group project presentation for Mechanics of Materials. These are my group members. Introduction. Structures are most critical importance in our daily lives since they provide the basis for buildings, bridges, and other infrastructures that must be safe, operational, and dependable. Before any construction process, there should be a detailed structural plan and analysis so that the design can effectively withstand anticipated loads and environmental factors without failure. Structural analysis is a basic instrument for civil engineering that integrates physics, geometry, and failure theory to evaluate the strength, stability, and behavior of structural systems.
Objective. They have three main objectives. The first one is to understand structural behavior through the practical use of structural analysis. Second one, to analyze and model frame structural members include beam of different support and load. The last one is to determine internal reaction, bending moment, shear force, and maximum stress and deflection through the manual calculation.
Methodology. Each selection of structure, each student in the group performs site visits to identify actual framed structures, including beams, columns, and slab systems in building, bridges, and public infrastructure. Second, schematic drawing. A simplified structural diagram is created based on the site observations and measurements. Load calculations. External forces exerted on the structure and assessed according to their intended purpose and material characteristics. Structural analysis using equilibrium equations and fundamental statistics principles to compute the support reactions, maximum shear force, and maximum bending moment. Stress analysis utilizing the computed internal forces, bending stress, shear stress, and maximum deflections, and ascertained through classical mechanics of material equations. Six, last one, deflection analysis. The maximum deflection of the structure is calculated under applied loading by using manual calculation method to evaluate the structure's adequacy and safety. That's all. Thank you.
Hi, my name is Kavitra Krishnan, and today I would like to share about the structure I selected for the analysis, a notice board holder located at College Kediaman Lower Campus, UTHM. As shown in the figure, the notice board holder is a simple yet functional structure that serves an important role in student communication and announcements. I chose this structure because of its practical application in everyday life, and more importantly because it provides a great opportunity to explore basic engineering principles in a real world setting. So, for the next slide, the load calculation synopsis. The load calculation for the notice board holder was conducted according to EN 1991 1-1 standards. The dead load consists of the self-weight of the horizontal beam and the weight of the steel galvanized corrugated sheeting. The self-weight was calculated as 0.385 kN per meter and the sheeting added 0.096 kN per meter, resulting in a total dead load of 0.481 kN per meter. The life load QK based on category 4 normal maintenance and repair was computed as 0.72 kN per meter. In addition, the wind load was determined using the wind pressure formula and contributed 0.93 kN per meter. The combined life and wind load yielded a total life load of 1.65 kN per meter. Using the ultimate state combination, the total design load was calculated, which is 3.12 kN per meter. This comprehensive load estimation ensures the structural safety of the notice board under expected service conditions. On this slide, I present the free body diagram of the horizontal beam. The total uniformly distributed load WL is 5.6 kN. Since the beam is simply supported at both ends and the load is symmetrical, the reaction at both supports are equal, which is 2.8 kN. Using moment equilibrium in point A, which is 2.8 kN. From this, we get the maximum shear force of 2.8 kN and the maximum bending moment of 1.26 kN per meter at midspan. So, this slide shows shear force diagram and bending moment diagram. Now moving to section properties of the beam. The beam cross section is 100 mm by 50 mm. We calculate the moment of inertia about both axes. About the x-axis, Ix is 4.16 times 10 power of negative 6 meter 4. About the y-axis, which is Iyy, is 1.04 times 10 power of negative 6 meter 4. Since Ix more than Iyy, we choose Ix, which is equals to 4.16 times 10 power of negative 6 meter 4 for bending calculation as it offers higher resistance. Using the bending moment value from earlier and Ixx, we compute the maximum bending stress. For the top fiber, which is negative 15,144 kN per meter square. For the bottom fiber, 15,144 kN per meter square. So the beam experiences tension at the bottom and compression at the top. Next is the shear stress in the beam calculated using shear stress max equals to 1.5 V over A, where V is 2.8 kN and A equals to 0.005 meter square, which is equals to 840 kN per meter square. So the maximum shear stress developed in the beam is 840 kN per meter square. Lastly, we determine the deflection and slope of the beam under load using standard beam formulas. For slope, which is 1.238 times 10 power of negative 3 radians, and for the deflection, 0.7 mm. The maximum deflection occurs at midspan with a value of 0.7 mm, which is within acceptable limits.
Selection of structure. The structure that I had selected, which is a beam at College Kadiyaman, Luwa campus, UTHM. This structure was selected mainly because of its practical application and the opportunity it provides to examine from an engineering standpoint the possibility of applying basic engineering principles to a real-life situation. The assumption of loads has been taken dead load as 4 kN per meter, and the schematic drawing is shown as below. From the schematic drawing, we derive the free body diagram and calculate support and reaction. From that, we do the cut section method to find the maximum moment, which is 1.045 kN meter. Moving on, from the values I got, I draw the SFT and BMD diagrams. After that, I did moment of inertia. I chose the value of Ixx, which is 2.08 times 10 to the power of 9, which is greater than Iyy. And then I calculate the maximum stress in a beam for the top section and the bottom section. Moving on, I calculate the maximum shear stress and draw the diagram. Moving on, I did the deflection analysis using double integration method. I got a value of 3.22 times 10 to the power of negative 9 meter.
Hello doctor, my name is Ravindran. The beam I selected for the analysis is a part of the beam from a bus stop. It is identified as a cantilever beam. They have only one support at the edge of the beam. It is fixed. They have a 4-point load. The distance between the every point load is the 0.55 meter. Firstly, I calculate that load and life load by using the European standard. The dead load I got is 0.578 kN per meter and life load is 0.785 kN per meter. For find the load combination, I using the formula 1.35 GK plus 1.5 QK. So I got 1.95 kN per meter. The load is the uniformly distributed over the beam. Nextly, I calculate the support reaction for the beam. They have two forces and one bending moment because it's fixed. So I calculate and I got the dy equals to 3.58 kilonewton, and then the moment I got is 3.79 kilonewton meter. To identify bending moment and shear force, I using the cut section method. I cut the beam into the three section. The first section is 0 to 0.55, second one is 0.55 to 1.1, and third one is 1.1 to 1.65. This is the diagram for the shear force and bending moment. From the diagram we can identify maximum shear force and bending moment. The maximum shear force is 4.28 kilonewton, and the maximum bending moment is 3.78 kilonewton meter. Before calculate the bending stress and shear force, we want to calculate centroid of the beam and moment of inertia. The centroid of beam I got is 0.03 meter, and moment of inertia is 3.36 10 power of negative 7. And then the bending stress, the maximum bending stress I got is 0.338 the power of 6 the compression, and tension is same value. And then shear force is 2 to 68.55 kilonewton over meter square. Last part, deflection analysis. I got the maximum deflection is 33.4 millimeter with 0.03 radius slope.
Hello, good day madam. I'm Santiswaran Sivaraja. As shown in figure 1, the structure I selected is fixed support beam. I choose this beam for its visibility and practice relevance. It allows us to clearly observe how loads are transferred and how support reaction occur in the actual engineering context. Next, we move on the load calculation summary. This step is essential to determine the types of force acting on the beam. We calculate both the dead load and live load acting on the structure. These values are crucial for computing support reaction and further structural response like shear force and bending moment. Based on the loads identified, we calculate the support reaction. Since this is a fixed beam, it has both vertical and horizontal reaction along with the moment at the fixed support. These reactions are foundation to the entire analysis as they influence internal force within the beam. To further analyze internal force, we applied the cut section method to derive the shear force diagram and bending moment diagram. This technique allows us to understand how shear and bending moment vary along length of the beam and helping us to identify critical points where the structure is most vulnerable. We also examined the beam's cross-sectional geometry, which is a T-section. Calculating the center of this section is essential for finding the moment of inertia. Finally, we determine the maximum bending stress, maximum shear stress, and maximum deflection of the beam under the applied loads.
Figure 1 shows the structure I had selected, which is a beam of canvas at welded UTHM. This structure was selected mainly because of its practical application and the opportunity it provides to examine from an engineering statements standpoint and the possibility of applying basic engineering principles into the real life situation. So this is the freeport diagram of the schematic drawing, which I had 5 kilonewton on the meter and 6 meters in the length. So in here I have calculated the reactions of calculation of support reactions, which I got 30 kilonewton. Support reactions in each sides 15 kilonewton by each side. So here's my stress, shear stress diagram, and also my bending moment diagram, which I got the maximum stress in the beam bottom is 198.8 kilonewton. In here I have calculated the maximum shear stress, which I take 1.5 of the VMA, then 1.5 times 15 divided by 0.8 times 0.3. Tmax is equal to 93.75 kilonewton meter square. Here it's the last part, which is deflection analysis, which I calculated the first the moment of reactions. Then I came to calculate the other deflections parts, which I've quietly arranged the calculation into the box of here, the paper. So as you can see here, I have got every value that's right. And that's all. Thank you very much.
In this study, we analyzed the deflection of 5 beams with different support types. Beam A, B, and E, which are simply supported or fixed-ended, had deflection well within their allowable limits, indicating safe performance. However, beam C and D, both cantilever beams, show excessive deflection beyond acceptable limits. This suggests a need for structural improvement or reinforcement to ensure safety and serviceability.
So, for the conclusion, the deflection analysis of 5 UTHM beams highlighted the importance of support type, span length, loading, cross-section, and material stiffness in structural performance. Beam A and B showed excellent behavior with minimal deflection due to effective design and support conditions. In contrast, beam C and D exceeded their deflection limit significantly, indicating under-design or excessive loading, which could compromise safety. Beam E performed within acceptable limits. Overall, the study emphasizes that proper deflection control is essential to ensure the safety and serviceability of structures. Thank you.